Good morning, good afternoon, and good evening. So we will have our first talk today from Professor Xingbo Zhao. He will talk about quantum simulations and life from quantization. Please proceed, Xingbo.
Okay. Thank you very much, Meiji, and I would like to thank all the organizers for giving me this precious opportunity to report our most, let's say, recent progress on studying, let's say, the pair production in strong field in both classical and the quantum approach, and since basically this we are just let's say starting in a starting stage of studying this topic using quantum approach. However, Meiji asked me, whatever we can have, let me talk about the let's say the quantum part of this project. So I think in this talk I will just basically talk a little bit about our, let's say, thinking on how to model this problem using quantum algorithm. So the quantum part of this project is very preliminary, and the classical part is basically based on the article we recently uploaded to archive. This one. So this work is mostly done with our graduate students and postdocs and our collaborators. So yeah, as I said, the topic is about pair production in strong field. So this is the outline of my talk. So how many minutes do I have actually?
You have 45 minutes.
45 minutes, okay.
Okay. With discussion, I can remind you when there are 10 minutes left if you want.
So yeah, this is the outline. So basically, the pair production has a famous name. It's called a Schwinger effect. So I will, in the first part of my talk, I will basically introduce a little bit of history and the physics of the Schwinger effect. And yeah, in the second part, I will basically talk about our method, which is called the TBFQ, time-dependent basis light from quantization. I will basically explain what it is. And in the third part, I will basically show the results of our numerical results of applying TBFQ method to study Schwinger effect, the pair production in strong field. And then in the fourth part, I will tell a little bit about our, let's say, most recent attempts of studying this topic using a quantum algorithm. Finally, I will conclude. So basically, the Schwinger effect is basically which means that a pair of fermion antifermion is created from vacuum in the presence of strong field. So this effect has a long history, and it was basically in the early days, one Oscar Klein found the interesting phenomena that when he tried to solve the Dirac equation in this simple, let's say, potential barrier, and he found a very interesting phenomenon, which is that usually we would think that if the potential is very high, then the particle will not be able to penetrate the potential, and it will just, how to say, bounce back. However, the interesting thing is that when the potential is large enough, so that is on the order of the mass of the fermion, actually the barrier starts becoming transparent, and which means the electron can penetrate through this very high potential. So this has long been a puzzle, and this puzzle, nowadays there are multiple ways to explain this puzzle. However, let's say the most, let's say, common, let's say, category of explaining this puzzle is basically through the pair production mechanism, which means that this is can be understood by the fact that in the small vicinity of this potential barrier, there's a very strong electric field we can think of. Then due to this strong field, then it creates a pair of, let's say, electron and positron, or in other words, let's say a pair of hole and let's say an electron. And then what happens is that the electron falls into the hole, and then the created let's say the created created electron continues to fly to the right. So it looks like as if that the electron just penetrates through the barrier. So yeah, this is a schematic figure that due to the existence of strong field, the mass gap between the Dirac sea and the fermion, the visible fermion, is get tilted, and so that allows that allows the spontaneous creation of fermion anti-fermion pair. So due to the effect of strong field. So I will also now explain why I choose this topic. That's also in some sense I understand this this workshop is about strong let's say about let's say hard probe or particle let's say or high energy nuclear physics. So in the one of the important things in high energy nuclear physics, particle because the energetic, let's say, collision, the particle creation is a very common phenomenon. So through this exercise, I also want to, let's say, illustrate that how we can have a, let's say, modern way to treat the particle production process, and explore the let's say the outlook of solving this problem on quantum computer or quantum algorithm. So this is a very classical, let's say, important particle creation process. So the rigorous or quantitative calculation has been done by Euler and Heisenberg later. They use the technique of effective Lagrangian of QED. Although this phenomena can be seen already in relativistic quantum mechanics, but the more rigorous treatment requires the QED, quantum electrodynamics. So it has to be done in the framework of quantum electrodynamics. So they use the so-called effective Lagrangian method, and they found that they calculated the vacuum to vacuum transition amplitude, and above they found that their result above some threshold value, this amplitude acquires imaginary part, and by using this kind of optical theorem, we know that the vacuum to vacuum transition, when it gets imaginary part, which means vacuum can decay. So in some sense, the vacuum, if in the process of strong field, the vacuum is not the vacuum. I mean the ground state of Hamiltonian anymore. The Hamiltonian of the system can have a, let's say, lower let's say eigenstate, which is the new vacuum, which is made of fermion anti-fermion pairs. So their their analytical results is take this form. This basically can be interpreted as the so-called vacuum decay the width or decay rate. However, by inspecting this form, it has a very peculiar point. Is that the energy actually appears in the denominator of exponential. So this peculiar feature is that if you want to calculate this vacuum decay rate by perturbation theory, so that you want to make expansion around the small field. So you want to use perturbation theory to calculate the electric field. You will find that you cannot do that, because if you want to do a Taylor expansion of this rate, let's say around the zero electric field, you will find that the coefficient of Taylor expansion at every order is exactly zero. So this is also a classical so-called non-perturbative effect. So in some sense, this effect cannot be calculated perturbatively. So it's a non-perturbative effect. So this is so physically this process is important because it's a particle production. It's by strong field, but also mathematically it's also very interesting that because it's a very classical famous non-perturbative effect which cannot be evaluated by perturbation theory. So so for this famous non-perturbative effect, I think since the 1959 Schwinger, let's say, finally formalized it. There are many newer, let's say, more modern, let's say, method to deal with this this approach, this process, and this result has been reproduced in many different algorithms, many different methods. However, one of the let's say problem is that most of methods are still can only deal with the uniform, let's say, distribution of strong field, the strong electric field. It can only be uniform. The reason why we are interested in the non-uniform background field is because those so-called, let's say, there are a bunch of, other than the string effect, there are a bunch of let's say, similar effects. Usually people call the strong field QED or strong field effects. People are interested in studying it or studying or realize them using strong laser facility or some other let's say, process which can generate a strong field, like from heavy ion collision. For example, if one can merge two heavy let's say nuclei, so that in the vicinity of two heavy nuclei, the field strength can be above the so-called Schwinger limit. So, however, so for those realistic experimental facility, they can only achieve let's say the strong field in some localized field. So usually it's, the strong field is kind of focused in both time and space. So in some sense, we need an approach which can handle the strong field effect with let's say, inhomogeneous background field. So yeah, about I think I want to say about a couple of words about the strong the string limit. So I just, as I said, because of the peculiar feature that the derivative of every order is zero. So we can see that this decay width has also strange trend that basically it's almost zero, or it grows very slowly before the background field strength reaches a critical value. So which is basically in this case is by dimensional analysis is a mass square of the fermion. So when it let's say, reaches this critical value, it suddenly increases. So this is also from this numerical trend. It also looks non-perturbative because perturbatively it's usually it will be proportional to let's say usually integer order of coupling constant. So perturbatively it's not so easy to simulate to get this kind of trend. Okay, so this is the background. As I said, this is an ideal case to study. Although it's in QED, but the physics also is very relevant for high energy nuclear physics. So because in high energy nuclear physics, like a relativistic heavy ion collision, you can also create strong field, either QED or color field. So the physics is very relevant, and it's because of the strong field, it's a non-perturbative effect. So then I will basically I'll introduce our theoretical approach how to deal with this phenomenon. So as I said, we want to create a method which deal with this, calculate this phenomena, but we should be able to deal with a non-homogeneous background field. So this our approach is based on the notion called light-front quantization, which was first proposed by Dirac. So the idea is that instead of the Europe, the equal time quantization, we quantize the quantum field theory on the light front, which is a three-dimensional surface in the four-dimensional space-time, which the light front is how to say indicated on this figure as a kind of surface which is tangential to the light cone. So all the events on the light front have the common light front time, which is denoted by x plus, which is chosen to be the linear superposition of the Euro time x0 and one of the spatial direction. Usually is we choose x3. So the benefit of light front quantization is that the obtained wave function is frame independent, because this is easy to understand, because this the events on all the events on the light front are light likely spaced. So which means if you boost to another frame, they are still on the equal, let's say, light front time. So there is no basically they are still equal time events. So unlike the equal time quantization, where so different events on the same, let's say, equal time surface may be at different time if you boost into another frame. So the light front quantization will give us a frame independent wave function, which is very convenient for studying relativistic let's say particles moving with the speed close to the speed of light. So it's very easy to convenient for us to study relativistic dynamics. So this is because of this feature, so this light front quantization can basically is very easy, is very convenient for describing relativistic quantum field theory. So sorry, relativistic quantum mechanics or quantum field theory. So in this sense, it makes the Hamiltonian formalism, like the wave function, the language of wave function, really useful and usable for relativistic system. So we can talk about the wave function. We can in the Hamiltonian framework, we can study particle creation, creation or annihilation. So this is why we choose the light front quantization. So it basically makes the it makes the Hamiltonian formalism useful for quantum field theory. So that's what we basically want to achieve. So so this is the method we are using is called the time-dependent basis light front quantization. So I'm so sorry that I should at least give the full name once. But this is basically, but although the name is very fancy, it looks very long, but the essentially thing it does is very simple. It's just, as I said, it's just solve the time-dependent Schrodinger equation for the light front. This is the light front time-dependent Schrodinger equation numerically. So this is basically all what it does. So this is basically the idea is we write down the Hamiltonian of the system and the light front Hamiltonian of the system in the existence of background field, and also we specify the initial state, and then we can time evolve it by applying the time evolution operator. Then we can obtain the wave function of the system at any later time. So this is the in this example, as a first study, we basically we have to let's say study it in a basis, in a finite basis, in a truncated basis, because it's a numerical method. So in this method, actually in this exercise, initial exercise, we actually the basis is made of made through Fox space expansion. We actually retain this let's say 5 Fox sectors. So the leading Fox sector is of course the vacuum, which is our starting point, the initial starting point. And then we have our basis space contains 1 pair, 2 pairs, 3 pairs, and 4 pairs of electron positron. And for the simplicity, we initially only retain the longitudinal degrees of freedom for each particle. And in the transverse direction, we just assume each particle take a Gaussian with packet of width b. So we essentially ignore the transverse dynamics. So yeah, I should back up in some sense. In the light front dynamics, there is a difference between longitudinal direction and the transverse direction. So the x0 plus x3 is defined as light front time. The other linear combination x0 minus x3 is defined as longitudinal time. Sorry, longitudinal coordinate, longitudinal direction, and the other two directions which do not participate in the transformation is usually identified as transverse direction. So the transverse direction is a little bit different in dynamics. So in this case, we only keep track of the longitudinal degrees of freedom. And right. And also, I just forgot to mention that there's another important advantage of light front quantization is that compared to the regular equal time quantization, the vacuum structure is much simpler. For example, so for massive particles, unlike the equal time quantization, they cannot mix with vacuum. So in this case, in the light front quantization, the important thing is the Fock vacuum is the vacuum of interacting theory. If in this theory we ignore as we let's say we are doing now, we ignore the massless particle like a photon. In this case, we ignore the dynamical photon in our basis. If all the particles in our basis are made of let's say massive particle, we basically the Fock vacuum is basically the vacuum of the interacting theory. So that's another advantage of light front quantization. The vacuum is very simple, so it's easy to study the particle production. Yeah, you don't need to worry about the particle that's mixed with the vacuum. Okay, then the question is, how do we get the light front Hamiltonian? The light front Hamiltonian is we can just get it from using the standard approach of Legendre transform. We again we get it from the Lagrangian, the ordinary QED Lagrangian in this case, and the light front let's say light front Hamiltonian of QED has these terms. It looks many terms, but they are not really not so many. In order to obtain this Hamiltonian, we have to also specify the gauge. Actually, in this case, we choose a light cone gauge, where the A plus is 0. All the component A mu plus is just the plus component is 0. The other component are non-zero. However, in this case, in this study, we truncate away the dynamic of photon. So although there are many terms, but a lot of terms will vanish in our Fock sector, in our basis truncation at this moment. So basically, those two terms we can basically divide them into two categories. So one category is they do not involve the curly A, which in curly A we denote the background field. So there are two types of A field. So one is the normal A, which denotes the dynamic photon field. The other one is curly A, which denotes the background field. Because in this case, the background field contains a lot of particles. So we have to write the background field using some classical ansatz. So using some classical field ansatz. So right, we ignore the dynamical, let's say, quantum photon field. So we only retain the classical field, classical background field. Yeah. So the Hamiltonian can be basically written into two parts: the P minus QED plus the extra background field, which involves a curly A. So in this preliminary study, we actually use a very simple ansatz for the background field. In this ansatz, we are using a background field which only depends on light front time and the longitudinal coordinate. So it's also in the longitudinal direction. It oscillates. It's basically it takes a cosine. Let's say it takes the cosine, let's say, form. So basically, in other words, you can view the background field have this kind of longitudinal momentum given by L. And this A field, if we work out if we work out the physical field, the electromagnetic field, we will find that actually it only corresponds to the easy field, because so yeah, and also I forgot to mention that it's non-zero only in the minus component. So it's so as I said, the A plus component is 0 by the choice of the gauge, and the A purple component is also choose to be 0, and the only non-zero component is a minus component, and basically it just reduces to an electric field in z direction. So only the electric field is non-zero. So here basically we make a simple sketch. So left figure is the A field. How the A field depends on the longitudinal coordinate A minus, and on the right hand basically is the red plot is the field EZ field as a function of x minus. As L longitudinal momentum increases, we can see that the oscillation frequency also increases. So basically, this is, but also, yeah, other than frequency, another important difference is for the field, EZ field. Actually, for the same A0 is a dimensionless quantity because the A field has a dimension of mass, which describe the strength of the A field. So yeah, so basically A0, 1, which means the A field is close to the strength of the Schwinger limit. So for the same A naught, actually, as EZ, the EZ also depends on the longitudinal momentum L. As L increases, we can see that the peak value of EZ also increases. Okay, this is the time profile. So we can also let's say append a time profile. So as a function of x plus. So basically, yeah, we in this study we will try to apply different time profile. Some let's say one is the baseline one is a constant one, which basically we just switch the field on and switch it off. So it's a switch on, switch off, let's say type. And also we can study some, let's say, sine function profile, time profile. So those time profile may be closer to a real world laser facility. Okay, I think as I mentioned, this as I mentioned, the background field actually within the current truncation and with this particular ancestor of the background field, model of background field, actually only 2 terms are left because we don't have the dynamical photon. We also, because of it's only non-zero for the minus component, so a lot of terms vanish. So actually only those 2 terms labeled by orange shade, they survive. And the matrix elements, we can calculate matrix elements in the chosen basis. Here we in the longitudinal direction we just use the momentum basis. The lambda denotes the helicity or spin of the electron and the positron. So basically we can see that the background field can do 2 things. One is pair production. So it can create a pair out of vacuum, make the transition between let's say 0 to 1 pair. Of course, it can also create, let's say, from 1 pair to 2 pairs, from 2 pair to 3 pair, and so on. Another thing it can do is basically it can accelerate or decelerate the existing electron or positron. So basically we have those matrix elements. Then now we can show the numerical results. So basically we have the Hamiltonian available in a matrix form. We can time evolve it. Initial state is a vacuum, and here we give the probability to find let's say each number of pairs as a function of time. So we can see that as time evolves, we first so the left panel is for the constant, let's say, background field. We just switch it on, and the field strength is it does not depend on time. So basically, we see that initially the 1 pair Fock sector is produced, is populated. So first, initially the background field, let's create one pair. And then after the one pair is produced, then it can produce, let's say, the two pair, let's say, the two pair Fock sector start being populated, and so on. So actually, one of the interesting thing is actually, actually after the, let's say, after higher pairs basically are populated, actually they are populated, actually the lower pairs, the probability of lower pairs actually decreases. That's because as higher, let's say, number of pairs produced, actually the probability of vacuum decreases. So there is no room, in some sense, no, let's say, the initial state, let's say, because one pair is usually created from the vacuum, but if the vacuum probability is exhausted, so actually the one pair probability will also decrease. So here, the shaded area actually corresponds to our truncation parameter. So as time evolves, we found that as, let's say, larger and larger pairs are produced, we can see that the results are not so stable with the truncation parameter, which means we need even a larger number of pairs. So, which also basically means that we should probably stop time evolution. So current basis size is only good up to some time. So here is something similar, but with let's say sinusoidal time profile. So basically, only the pair production is a little bit slower in the beginning compared to the immediately switch on mode. Okay, so here is one thing, because one of the central puzzle for the Schwinger effect is because it's a non-perturbative effect, which means, as I illustrate, so which means the production rate actually is very small. I mean, if the background field, the strength is below some threshold, and it suddenly opens up. So then the natural question is how to understand this phenomenon in a time-dependent approach. How to understand it? So how to understand it in a time-dependent, let's say, Hamiltonian approach. So we study the production rate, or in some sense the vacuum decay rate, like 1 minus the production rate. So as a function of time. So we found interestingly, we found the following phenomena. So whenever, I mean, if the background field strength is below some threshold, at a small value, we found that the vacuum decay rate actually it oscillates with time. So so here we tried the three different, let's say, background field strength. They basically after some, let's say, scaling, so they overlap with each other. Actually, they not only overlap with each other. Actually, the results also coincide with leading all the time-dependent perturbation theory. So it can be determined by perturbation theory. So actually, however, what is interesting is that above some threshold, like in not 1, we found the vacuum decay rate. Actually, the periodicity actually get lost. So which can be seen from this figure. So like the black line here is basically the black line on the left side. So basically, you can see it's still also quasi-periodic. However, as you increase the field strength further, suddenly at some threshold like 0.5, around 0.5, the blue dotted line, we can see that the periodicity is basically getting loose. You can see that the vacuum decay rate above 0 has a larger area compared to the vacuum decay rate below 0. So this means that the vacuum decay or pair production rate can quickly accumulate with time. And if we further increase A naught, we can see that this phenomenon is more obvious. So we conjecture that in this approach, we can see that the reason Y is basically due to some non-perturbative effect at some threshold, actually the periodicity get lost. So that's explained. Otherwise, it's very difficult to understand because the first order, leading, second order, third order, they all scale with is zero. How can you get the behavior that is almost zero and it suddenly goes up after some threshold? So basically, then it offers this phenomenon offers a natural explanation. So basically, actually, the amplitude of this production is actually a scale with A0 square of to the higher power, no problem. However, below some threshold, actually the amplitude periodically oscillate. So the production rate cancels with the annihilation rate. So the net production is very small. However, above some threshold, the periodicity get lost. So actually in the long run, the production rate get quickly accumulated.
Oh, okay, so sorry to interrupt, Xingbo. We have less than 10 minutes left, and we also need to have a discussion. So maybe
let's. I think that basically, I think let me quickly go through this the other part. I think these are not so important. These are just basically we just study the per production rate at different let's say background field strength, different background field frequency, etc. Let me just quickly skip this part. Okay, let me talk a little bit about this quantum part. So the one of the feature of this time-dependent basis light quantum quantization is that we not only aim for describe the realistic background field with realistic space-time dependence, but the most important thing is in this method one can see that it in some sense it let's say retains the information of the wave function of all the produced particles. That's a distinguishing feature. So basically, we can track the wave function can track the motion of all the particles. Let's say 5 pairs or 6 pairs of the fermion and as any fermion. So the wave function contains very rich information of the dynamics. So as a number of pairs, let's say increases, I think the complexity quickly proliferate. So in this case, if we want to have a realistic description of let's say particle production in relativistic heavy ion collision, for example, we need a quantum computer. So we need the classical computer may not be enough. So only the quantum computer can basically accommodate the proliferating number of particles. So the reason why I think I will also let's say skip this slide, which just tell us about this some mainstream let's say realization of quantum computers. But the reason I want the most important thing I want to tell is the reason why quantum computing can have the potential to support a much larger Hilbert space or much larger number of particles, because different from classical computers, quantum computers actually use the notion so-called qubit. So the classical computer, every bit has only 2 states. One is 0, the other one is 1. However, in each qubit, the quantum computer have this
I think we lose the connection to Xingbo. Xingbo, can you still hear us?
I think
your image freezes. Can you hear? No. Okay. Oh, you can hear. Okay, Xingbo can hear us. No, we cannot hear you, Xingbo. And your screen freezes. Yeah, okay. Let's wait for you to reconnect. Okay, sorry everyone, there's some technical issue. Xingbo will reconnect. Okay, I see Xingbo is back. It's connecting. Hi, Xingbo, can you hear us? I see you are here, but I did not see your screen. Oh, you can hear me. Okay. Maybe you can try share your slides again to see if that works. Okay. Oh, Xingbo, but we cannot hear you. Are you speaking? We cannot hear you.
Hello, can you hear me?
Yes, we can see you and hear you.
I'm so sorry for the trouble. I'm so sorry.
No problem. It's not your fault.
I'm so sorry. So basically, let me speed up. Okay, so basically, the idea is the quantum the computing has this qubit which can store enormously more information compared to the classical bits. Okay, so this is some let's say basics about quantum let's say gates. I think let's skip that. Okay, so so here again in the essential how to say essential idea for quantum simulation of the time-dependent basis like from quantization is basically we have to the core of the TBLFQ is the time evolution let's say operation. So on a quantum computer currently we choose this trotterization scheme. So basically we can so because the quantum is currently it's relatively easy to implement the unitary because the quantum gate quantum gates can only implement a unitary transformation. So the idea is we want to reduce the time evolution operator into a bunch of unitary operation so that we can make use of the quantum gates to implement the time evolution operator. So the idea is that so basically the idea is that so in each time step we have to basically try to break down the Hamiltonian into each small let's say step, and and actually we have to choose a appropriate basis. However, currently there is a problem because our interaction in this case actually is not diagonal because the interaction I do remember the interaction will create pairs, so it will make a transition from vacuum to a pair of electron positron and from one pair to two pairs, etc. So it's not diagonal. So actually we actually in this process in the initial study we actually have to manually diagonalize, find a basis where the V int, the interaction Hamiltonian, is diagonal. So this part is currently actually done on a classical computer. We have to use a classical computer to diagonalize, find a basis to diagonalize the interaction part. Then we can cast this time evolution operator into a bunch of unitary, let's say, not only unitary but also actually diagonal matrix like this. So this, if each step in the trotterization takes this form, and then it can be realized on a quantum, let's say, gates. So this is the idea. Then basically, these are very preliminary results. So basically, the different color lines are actually the probability of finding pairs calculated on classical computers, and actually the final at 5 inverse MEV, the final solid dots actually we calculate using the trotterization quantum scheme implemented on realized on a Qiskit simulator. So basically, we can see that the quantum computing results agree with the classical algorithm. So this brings me to the conclusion. So basically, so the method, the time-dependent basis latent from the quantization. So it basically it allows for the treatment of background field with arbitrary space-time dependencies, and it's based on quantum field theory. It can simulate particle production, and it's basically it's a many-body approach. So the wave function contains information of all the individual particles, and for the classical part, I think the most interesting part is from this study, at least it offers a picture to understand the famous Schwinger result that that the production rate is a non-perturbative phenomenon, which is that the production rate goes suddenly up at some threshold value, which is called a Schwinger limit. So above the Schwinger limit, it suddenly goes up. So from this TBFQ method, we can understand how it happens through a time-dependent way. So basically, it's not because the amplitude, actually the production amplitude actually has a sudden threshold. Actually, because above some threshold, actually some higher order transitions are very important, which breaks the periodicity so that the production rate can quickly accumulate with time. Finally, I want to say that the time-dependent basis from quantization is natively very friendly to quantum algorithm because it's based on Hamiltonian formalism, but for quantum field theory. So it can be friendly to quantum algorithm. And also another thing is that when we apply it to fundamental interaction, like the fundamental QED or QCD background field, it has very nice features. Actually, in the fundamental interaction, the background field, the V, actually is very simple. It's only at most it is usually two-body interaction. So it's like from 0 to 2 or from 1 to 3, etc. So in this sense, the interaction is actually very sparse in the Fock basis. That is also that basically creates a lot of opportunity for quantum algorithm. So it has a lot of large room for let's say optimization. So we can easily find a quantum algorithm which can be realized on the real quantum computers, and it can there are a large room for optimizing the efficiency. Finally, I would say that the TBFQ method is also in some sense necessitates the quantum computer, because the advantage of it is it can simultaneously keep track of many particles. Then in order to, let's say, demonstrate its advantage, we need to simultaneously keep track of many particles, and then the Hilbert space, the dimension of Hilbert space get quickly very large. So that's in this sense, it's a natural, in some sense, application of quantum algorithms, so that we can use by using quantum computers and TBFQ, we can have a very accurate study to understand the, let's say, relativistic collision process, the particle creation process, and study the correlation among the produced particles. I think that's it. Thank you so much for your attention.
Thank you very much, Xingbo, for the nice and interesting talk. Do you have any questions from the audience? If you have a question, you can just raise up your hand. Okay, I don't see it has now. Okay, maybe I will start with my question. So when you talk about the quantum simulation, for the you mentioned the diagonalization of the interaction Hamiltonian part. So you said it would be easier to implement if the interaction Hamiltonian is diagonal, right? So
correct.
Yeah, I want to understand. So what's the difficulty on the if the interaction Hamiltonian is not a diagonal? Is not diagonal. Is that because the quantum circuit, the quantum gate would be very complicated for non-diagonal Hamiltonian, or we do not know how to.
Yeah, actually, this part, to be honest, is done by our collaborator. But from our collaborator, actually, actually, the thing is, yeah, the difficulty is in the part of quantum circuit. Let's say quantum circuit design. So currently, the problem is as far as I know, there is no standard quantum circuit to realize the arbitrary, let's say, a matrix vector or matrix multiplication. So we cannot do the exactly same thing as we did in classical on classical computers. So basically, unless this kind of very special form, so currently the quantum computer is not powerful enough, or quantum algorithm is not powerful enough to efficiently realize arbitrary matrix multiplication. That's basically my understanding.
Okay, thank you very much. Okay.
Yeah, from our collaborators, actually, even the arithmetic basic arithmetic calculation on quantum computers are not so trivial. Actually, at this moment.
Okay. Thanks.
Okay.
Okay. We have a question. Someone hands up. Okay. Maybe allow me to have a second question. So in the beginning, we will talk about the Schwinger effect, and you formulate the background field, the A minus dependence on X minus and X plus, right? So X plus is the life from time, and the X longitudinal direction. So does this mean that this background field is a one-dimensional background field?
The dimension, because it's QED, so the QED can only live in the 3+1 space.
Okay.
So it does not depend on X perp, which means it's uniform on the in the transverse directions.
Oh, so in the transverse direction, there's no barrier. Should I understand that way?
Correct.
So there's okay. So okay. Let me see.
I have another question. So in one of your plots, you show the contribution from 1 pair, 2 pair, 3 pairs, and I was missing. Is there a contribution from 0 pairs?
Actually,
or how I should understand the line that says all?
Right. So basically, you can think, yeah. So basically, the contribution from 0 pair is 1 minus all. So basically,
Okay.
1 minus all is the contribution from 0 pair.
Oh, okay. So it means that at the last time, the 0 pair probability disappears. So it's a
Correct.
Okay.
Correct.
Thank you. I don't see any hands raised up.
Okay.
So thank you again, Xingbo, for the very
No
nice.
problem. Thank you so much for giving me this opportunity to present our research. Thank you.
Thank you. So so next we will have a break, and we will come back in about 20 minutes for the next talk. Okay. Thank you very much all. See you then.